So what I should request of first things when you read them, your chocolates are on the desk under your Oh, they are chocolate for all these classes. I bought chocolate on my own. So I bought 2 boxes. One was so you never choose nothing by eating it all.
Good afternoon, everybody. I'm glad you all made it here to Copenhagen, and I hope you will all enjoy the Cosmic Ray meeting. Certainly I'm very much interested in what you all have to say, and I'm looking very much forward to the discussions in particular, which then means, of course, that it should be in everybody's interest to stick to the time of the allocated talk in favor of having the possibility of a full length discussion. Let me say a few words about Nordita, the institute where we are, which sponsors this meeting. Nordita was founded in some long time ago, 1957, I believe. It was at a time when many of the European big centers, like CERN, for example, did not exist, and it was founded by Niels Bohr at the time, who thought something like a center, which now became something like CERN, of course, should be situated perhaps in Copenhagen. But that was not the case. So CERN was founded in Geneva, which then meant that there was still a very strong need in the Nordic countries to have something like a center for physicists, especially theoretical physicists. And that was indeed the case, and so Niels Bohr was able to found this institute with the funds from the various different Nordic countries. So the mission of the institute has therefore always been to serve somehow the needs of the Nordic countries, whatever they are, because they are changing as time goes on, and we are all the time readdressing and thinking about the issue of what is the need of the physicists in the different Nordic countries. It was a time, for example, when a postdoc program as such did not exist in the Nordic countries, and so Nordita was the only place at the time where postdocs could be funded, and so therefore there was a great influx from the various Nordic countries to Nordita to come here as a postdoc to learn other physicists, to get in touch with other physicists, and Copenhagen was always a place of a big influx of visitors from all around the world. So this is the reason why Nordita indeed was quite successful in serving this purpose of helping the young Nordic scientists in particular, but also the established ones, to connect to the rest of the world. Things have, of course, changed a little bit in the sense that now many different countries have their own postdoc programs, so we have seen a little bit of a decrease in the number of applications for the Nordic fellows, as they are called, but we still always have a larger number than we can actually take for the fellows. So this means the fellows that we have at Nordita are mostly all from the Nordic countries. We do have occasionally fellows from postdocs from other countries, but that is typically only working based on funds from either the European Union or from the local governments of the country where the people come from. Occasionally we do have also extra money that we can use for international postdocs. So in addition to the postdocs, Nordita has a program for Nordic assistant professors, which is very similar in scope to the Nordic fellows, except this is for more senior people. So this is for people who want to get back from a series of different postdoc positions at different countries, want to get back to the Nordic countries, want to find a permanent position. And in fact, those Nordic assistant professors always had a very good record in finding a permanent job, mostly in research in the Nordic countries. In addition to that, we have, of course, the rest of the faculty, which consists of 6 permanent professors plus something like 4 assistant professors, both groups are typically internationally staffed. There's no restriction on nationality. So this is about the situation of Nordita as it is here, but Nordita, of course, spreads around the Nordic countries. It has, we have a whole network of people which, of course, is automatically established through the fact that many of the people who are now over the history of 40, 50 years having permanent positions in the Nordic countries, almost all of them, or a large fraction of these, at least theoretical physicists in the Nordic countries, have a record of having been at Nordita at one point or the other. And this is a very comforting feeling to somehow know that all the different people have actually something like a common basis somehow. And so this provides still a network for Nordita. It can be sometimes used, for example, in the sense that many of the decisions that are being made in Nordita are being made from a Nordic board, and many of the board members at one point or the other, some 20 years earlier, have been a fellow at Nordita. This was then the network aspect, and in addition to this, there's a lot of other programs. For example, we have a program called corresponding fellows. Corresponding fellows are people in the Nordic countries who are employed permanently at some other universities. They are typically more senior people, but they can play a role at Nordita by visiting Nordita for extended periods of time, and then also participate in the faculty meetings and have some say in the organization of Nordita in the future. That was the corresponding fellows. Then we have a program called Nordic Projects, and that's also a very interesting program which allows, these are projects for a period of 3 years. They can be proposed by people typically either from Nordita or from one of the Nordic fellows. This allows the people to run, for example, a series of meetings over a period of 3 years. So these will be the application deadlines once a year in the fall for these Nordic projects. At the moment, we have a number of different Nordic projects running in the fields of condensed matter physics, high energy physics, astrophysics. There we have 2 projects at the moment, one in high energy astrophysics and another one in astrobiology. In both cases, in all these cases, we typically have something like 1 or 2 meetings per year, which also helps establishing a network of Nordic researchers, which then have also some contact, of course, with overlap at least with other scientists from other countries. Now, the purpose of this meeting is certainly to talk about cosmic rays, cosmic ray propagation, evolution in the galaxy. Now, this has many different important aspects, as we will hear throughout the meeting. Those of you who have seen the Discovery Channel recently have heard the very interesting presentation where Gary Glassmeyer, who many of you will know, showed up with his simulations of the geodynamo. He was talking about the reversals of the possible, rather soon, reversal of the Earth magnetic field. The observational evidence that this may or may not happen within the next 100 years. If that's the case, one really now needs to start to worry about this, because certainly the impact of cosmic rays on the health of life, or health of people, of course, is undoubtedly very clear. But we also have, and we'll hear this later during the meeting, some influence through the cosmic rays on the climate, which is very important, and we will hear more about this tomorrow at a talk by Henrik Svensmark. Now, this is now another historical reason why we had this meeting here was this. It was basically last autumn that we came to this idea. The reason was that David Moss and Anwar Shukurov and a few others were continuing one of their applications for visiting fellowships to NASA. And NASA supported these grants over the last 2 or 3 times, and so there was a call for another prolongation of these visiting fellowships, or visiting money for visits, and after 2 weeks after the deadline of the call, after everything was finished, they actually changed the announcement. So they all of a sudden say
NATO.
It was NATO. Yes, sorry.
I had the same.
And you had the same. Many of you had the same experience. And so this was, of course, quite a scandal that all of a sudden you invite applications, which is almost an offer of a contract in some sense, and all of a sudden you withdraw. And NATO is apparently in a high enough position to do a thing like that. So this was quite a shock. But this came at a time when I thought, okay, if you want to get some people together, then here we can certainly help out. And I think that was one of the reasons for running this meeting at this time of the year. So the first chairman of today is Andrew Shukura. We will have 2 talks, Andrew Strong and Misha Hanash. And I give now the word to Andrew, please.
Thank you, Arthur. Thank you for organizing this meeting. I think we shall have many opportunities to thank you again for this. But now let's turn to the talks. So the first talk is Andrew Strong. It's on modeling cosmic rays and gamma rays. So half an hour.
Okay. So thank you very much to the organisers for inviting me, and hopefully this has some relevance to this meeting. So I will talk about modelling cosmic rays and gamma rays. So I've been looking at for the last few minutes. This is work done mainly with Igor Moskalenko at NASA and Olaf Reimer at Bochum, and some work also from Seth Dieter at Stanford. And it's concerned, as the title said, with the propagation of cosmic rays in the galaxy and their relationship to gamma rays. And this is, of course, complicated business, because we have the galaxy here, we have lots of things happening. We have the sources being injected, the cosmic rays propagating, various things going on like energy loss, reacceleration, production of secondaries, interaction with gas, interstellar radiation field, ISRF, and eventually you escape, after doing all these things, escaping out into intergalactic space. So what we're trying to do is to model this as accurately as we can. In fact, we take almost an engineering approach as our idea. The idea is to try and use all the information we have to make a model of this. And here in more detail is what's going on, at least in our conception. We basically have cosmic ray sources, which are usually thought to be supernova remnants, diffusive acceleration by shocks and supernova remnants. They produce primaries, mainly protons, but then all the other heavier nuclei, and electrons, of course. And these propagate in the galaxy. The type of process is a diffusion, convection, and reacceleration, which we're considering. And they interact with the gas, the neutral gas, the molecular gas, and the ionized gas. They lose energy with the gas, and they also fragment on the gas. And then they make secondaries, things like beryllium-10, beryllium, boron, and so forth, which can all be measured at the Earth. And then secondary electrons and positrons, and also secondary antiprotons. And they do that, and these are the things we can measure locally. And then, of course, these things, by the same interactions, then produce also pion decay, gamma rays, and by Bremsstrahlung, the electrons produce gamma rays also by inverse Compton emission. And these can be measured by instruments like the Compton Gamma Ray Observatory, and in the future GLASS. So they're the things we can measure in those ways, but they also, of course, we have the interstellar radiation field, optical and far infrared, and the CMB. And this also causes energy losses for the electrons, and also generates inverse Compton gamma rays. So all these things are somehow connected. And the final thing on this picture then is the electrons interacting with the magnetic field, losing energy and generated synchrotron. So that gives another observable we can use to constrain models. So the basic idea, the whole goal was, which has been going on, we've been working on for many years now really, is to use all types of data at the same time in a self-consistent way to test models. So there's no really very high-powered theory here, in fact. I mean, the model is rather phenomenological, but the idea is to try and use all the data we have. So what we observe near the sun, like primary spectra, protons and so forth, like this one, protons. We observe the secondaries, we observe especially these ratios, like secondary to primary V to C. We observe secondary secondary positrons and secondary antiprotons, typical of the things we can observe in the heliosphere. But we shouldn't just concentrate on that, because we observe from the whole galaxy with instruments like EGRET, the distribution of cosmic rays over in the galactic plane from the Milky Way, and also, for example, from COMTEL at lower energies, another space telescope, another space type of observatory. And then, of course, last but not least, the synchrotron emission, which is telling us about the electrons. So all of these are somehow connected together, and we want to make a self-consistent model of that. And it turns out actually not to be that easy to fit everything, as we shall see. So the basic idea for the cosmic ray propagation is, probably most of this is rather familiar. This is just a cosmic ray propagation equation. The rate of change is just the cosmic ray sources as a function of position and momentum. I use momentum everywhere here. Either primaries or secondaries. Secondaries are produced just by the action of the primaries on the gas. And then the kind of processes there are just spatial diffusion, this term here, and convection. And then perhaps possibly less familiar to you is the diffusive reacceleration, which is just diffusion in energy space. And the idea being that if you have diffusion, which is due to scattering on magnetic irregularities or whatever, and if those things are moving, then you simply can't avoid that you get some diffusion in momentum. And this is what is called the minimum diffusive reacceleration. It's the reacceleration you've just got to have at some level. And to first order, there's a relation here between the diffusion in momentum space and the diffusion in real space. Then we have the other processes which are essentially trivial: the momentum loss by ionization and Bremsstrahlung, adiabatic momentum loss if you have a wind. And then for the nuclei, they actually get fragmented. So there's this term which is fragmentation, and then there's also the radioactive nuclei which decay. So the idea is to solve all of this. And the way it's done is by this program called Galprop, which we've developed over the last 10 years, which is basically solving that numerically on a 2D or 3D grid, time-dependent or time-independent. And the idea is you start off then with primary source functions, which have, of course, source abundances, which can be taken from solar abundances or whatever, and spectra. And then we propagate the primaries, and that gives us the primary distribution in the whole galaxy as a function of energy and space. And then from that we can then compute the source functions for all the secondaries, like beryllium and so forth, and the antiprotons, using the primaries and the gas distribution, which we try and make as realistic as possible. And then we propagate the secondaries. And then if we want, we can also then make the tertiaries, which are the secondaries just making more secondaries, tertiary propagation. So then we have the distribution of the things which we can measure directly. And the last thing then is to calculate from the same model the gamma rays via the various processes, inverse Compton, ion decay, and so forth, and the radio spectrum. And then compare all that a lot with the data. So Galprop again it has a 3D gas model based on astronomical surveys like H1, like CO, cosmic ray sources, which is more or less a model, interstellar radiation field, which is very important for the energy losses of electrons, and for inverse Compton, which we have as a function of position and wavelength. Nuclear cross-section database, of course, very important. Not all these cross-sections are well known, and they're energy dependent, so that's a big thing. Energy loss process is essentially simple. A BFE model, which actually we haven't really done very much work on. I want to learn something at this talk, at this conference, maybe, how we can improve. We had a very simple model for the magnetic field up to now. And solar modulation has, of course, to be considered and used. And then we have the gamma ray processes. And this code is now, we've actually had it publicly available since we started. And it's been written up in various papers, the most recent is papers concentrating on the gamma rays from this year. So that's Galprop. And the standard model we tend to use is actually really quite simple. It has a halo with a sharp boundary and free escape into interstellar space at the edge. Diffusion with a Kolmogorov type of form like this, which I'll talk about more later. Diffusive reacceleration at some level with this kind of parameter, alpha and speed. And at the moment, although we have considered it convection, we haven't used so much, but we ought to, because we know there's a galactic loop. Okay, so now I'll talk about the testing of this and how we can actually use it to get some. Basically, one of the most important things we measure is this secondary primary ratio, B to C. There's almost no primary boron, and so the B to C ratio is a very important thing which one measures with balloons and space experiments. And now in a simple diffusion model, it's actually very simple what you expect. If you have a diffusion coefficient just going as beta, which is just the velocity times p to the alpha, the time to get out to the halo, to escape, is something like the square root of dt. And that simply gives them t is given by this, and b to c, when you just write down the product of the cross-section and the time, it simply comes out to p to the minus alpha, like that. So that is what you might naively expect for the b to c ratio as a function of energy. We have a simple change like that. Now, is that what we observe? Actually not. What you see for the B to C ratio is indeed something falling off with a power, actually more like 0.6. But it turns down at low energies, and this is more or less a puzzle, which hasn't really, well, some solutions which I'll talk about, but it's a puzzle that we really expect naively the thing to keep coming up. A simple diffusion model. So what can we... One possibility is that one simply has convection. If you have a wind, then the particles will have a constant time to get out at low energies, and then the B to C would be something just like the velocity, and it would just flatten off. And this does help a little bit, but actually it turns out that it's very hard to really get a bump in this ratio. It flattens off, but convection doesn't really seem to be able to do it. And the conventional approach, in fact, which most cosmic ray people working in cosmic ray field tend to use when they're getting primary abundances, for example, is simply to be ad hoc and simply make a break, an ad hoc break in diffusion coefficient. It's like this, and then of course one can reproduce the data and use it to get source abundances and everything, but it's just ad hoc, doesn't have any physical origin, but is what's normally used in people working, say, with leaky plasma. Not really very satisfactory. Okay, but what seems to be a better solution, what we've really tend to believe now, is this is really a result of reacceleration. If you put in reacceleration with something like a Kolmogorov spectrum like this of the diffusion, what happens is the energy dependence of the diffusion in momentum space causes actually an energy dependent, produces a bump in the particle spectrum like this, just because the higher energy ones get progressively less accelerated relative to the lower energy ones. And you actually get a bump in all the cosmic ray spectrum, and the result is, when you compute it, an actual bump in the B to C ratio. This is before solar modulation, by the way, and this is after. So by putting in actually quite reasonable numbers like alpha and speed of 30 kilometers per second, and using the relation between dxx and dpp, that actually can fit reasonably well. So it seems to be a reasonable solution. There are other actual ways of getting the B to C ratio, which we published in 2003. In fact, another way is to assume we're near a local source of primary cosmic rays. For example, the local bubble is a very good candidate for that. We know we're sitting in a local bubble. It probably has accelerated cosmic rays, at least in the past. So if you have a local source of primary carbon, but the secondaries are still coming from the whole galaxy, the turns out that when if you assume something like this, you can also get it fixed. So there are other ways of getting this done. Okay, now turning to something else, which is the size of the halo region. Basically, we get limits on that by the radioactive nuclei like beryllium-10, which has a lifetime of 10 to the 6 years. And so the faster the longer the cosmic rays take to escape, the more they tend to decay. And so as the halo gets larger and larger, they get more and more decayed. And so, for example, between 2 kiloparsec and a 10 kiloparsec halo, you have a change in the amount of beryllium-10 relative to the stable beryllium-9. So you can actually make limits on the size of the halo from 4 different radioactive nuclei, and this is what we did in 2001. We actually derived some kind of range on the halo size, just assuming this very simple, naive model that the halo really has a sort of means something and has a sort of sharp boundary, and go and gets limits on the size of the halo. So it has to be quite large. And this is just some more examples of those 4 radioactive nuclei, all of them more or less consistent with the 4 kiloparsec size of the halo. And very recently, in fact, this just appeared in August after the results from the ISOMAX experiment, which is a superconducting magnet. They were able to measure right out to about 2 GeV, which before one had only data points here. So you start to see the rise just due to the gamma, just due to the Lorentz factor, making the lifetime of the beryllium-10 longer. And that again now can begin to be compared with models. Maybe the 4 kiloparsec is getting on the edge of this now. So unfortunately, this thing failed in the second flight, and they would have had very much data by now, very much better data. But unfortunately, this is the data we have for the next time. But it's very nice to see this. That experiment, okay, ISOMAX. So now another very good test is of course not just the B-to-C ratio, but particles like positrons and antiprotons, which are secondaries. So there are better and better measurements of these now, and I'll come back to that. And the point is that they're produced in proton-proton collisions just like gamma rays. So if you measure these things locally at the Earth, that they're related to what you see over the whole galaxy in gamma rays. So we have a constraint there. Another thing you can do, I won't talk about this much, is to get the cosmic ray elemental and isotopic abundances out, and then go back and, by comparing with the data, this just shows the abundance as a function of charge as computed. By comparing this with the observations, you can go back and get the source abundances. Okay, what perhaps has more relevance to this meeting is the synchrotron aspect, which we haven't really devoted very much attention to actually. But we have got it in and in our paper in 2000 we compared basically we made a model of the B field with just this simple formula here, the slow fall off with radius and a 2 kiloparsec exponential decay in Z. And we basically, what we were doing then is getting the electrons, because it depends of course on the cosmic ray electrons, were based on the analysis of the egret gamma rays. So we know the radial distribution of electrons from that, and then we can go back and see what variation of B we need to reproduce, for example, here the 408 megahertz Hasselmet house survey with an active plane. And we at the time, I mean, we're satisfied with this fit. We weren't trying to get all the spiral arms and individual sources here. Just from this simple form, we were able to get a satisfactory fit, and also that's that longitude. So along the galactic plane, and this is latitude. So this is getting into the galactic halo. But there's actually a lot more could be done here. We haven't really exploited the data. Here's actually the form of the galactic magnetic field with radius compared with another paper from the Durham group in 1990. Okay, another thing you can do is the spectral index, not just the distribution of the spatial distribution, but the spectral index distribution. And this constrains, in fact, we're getting better and better data on the spectral index of synchrotron radiation from low frequencies right up now and more to high frequencies, of course, from WMAP and so forth. And in fact here, in this work, we simply compared what we needed from the gamma rays, the electrons, would produce this variation of synchrotron index. So it was consistent, but actually not very constraining. And hopefully better radioastronomical data will improve and allow us to redo this kind of analysis, especially at high energies where WMAP and so forth are beginning to give very nice data in that range. It's high frequencies. Okay, now coming back to the gamma rays, and there's basically a problem here, and I'll describe how it's gone now. We basically started off with what we call a conventional model. We want to model the gamma rays which we see. And so we start off what we call a conventional model, which is just taking the protons and electrons which we measure at the Earth, the red line, and trying to predict the gamma rays. And this is a result which is actually known for a long time. This is the gamma rays measured by egret in the inner galaxy, and this is what we predict. And there's an excess of about a factor of 2 or 3. There's an excess, and the excess won't go away. The gamma ray, the cosmic ray data got better, and the modelling got better, but the excess is there. So it's trying to tell us something the models don't actually work. Well, the simplest possible naive model doesn't work. It just doesn't predict this maximum here. So what's going on? There's actually various ways you can think of. One is that we're not really seeing diffuse cosmic rays, we're seeing supernova remnants. It's harder. You're really seeing the cosmic ray injection spectrum. Another thing is maybe the nucleon spectrum in the galaxy is harder than we observe locally. Or the same thing for the electrons. Maybe what we observe locally near the sun is just not typical. And then what we think is that we can do it with moderate changes. I'll say that at the end. And some other people want something more exciting and exotic like dark matter. And maybe if none of these turn out to work, this would be, of course, more interesting. But let's see. So this is the point. You can look for this excess all over the sky. This is the egret map of the sky. And in fact, when you compare with the model, you find that the excess is always there. It doesn't matter if you look at lower latitudes, the anti-center, intermediate latitudes, you always have more than you expect. And that kind of rules out the first explanation, because if it's supernova remnants, you expect that excess to be only in the galactic plane. This seems to be a test of that idea, which at least it might explain some of it, but it can't explain all of it. So this would give an excess of low latitudes, but we observe it everywhere. So no. Another possibility, hard proton injection spectrum. The protons have a hard spectrum in the galaxy, and then we would get this excess of GeV gamma rays. So there's a test of that, because if you, as I said before, if you make gamma rays, you also make antiprotons, and you make positrons, and you measure antiprotons from these secondary peak-peak collisions. And this is what you predict on. This is what you would need to get the gamma ray excess, and this is what you observe in the antiprotons. So you would get too many antiprotons. So it seems not possible to get this GeV excess from the hard proton spectrum. And this illustrates the advantage of combining this analysis with particles and the gamma rays. Another way is to do it by a hard electron spectrum like this. So you say what we observe at the Earth is like this, but in fact the reality out there on average is something much flatter. Could be. But in fact, when we compare with egret data, such a model really gives something really rather different from what we observe. And in fact, there's more egret data out here than had been considered before, going right up to 50 GeV, and it really looks different. So we don't think that this is the solution either. Just to illustrate that, in fact, I mean, the electrons, because they have very high energy losses, they're not uniform, they're fluctuating all over the place because of the fact that the sources are stochastic. So it could be that we measure this, but the average is somewhere out here. But this effect is just not large enough. Okay, so that's noted that one. So I come back to what we think is the solution, in fact, what we call the optimized model. We simply take the proton. We say that what we observe in the proton and electrons locally are not typical, but the difference is a factor of 2 or 3. So This is what we observe, but the average galacticon is something like the red line, and something similar for electrons. So a sort of rather mild, not too large change in the proton and electron spectra. And then when you do that, you can actually construct a model which agrees reasonably well with the egret data. Maybe not the highest point, but that's pretty uncertain data. So we can actually get rid of this GeV bump by rather moderate changes in the cosmic ray spectrum. So maybe this is the truth, but maybe it's more just an existence proof that it can be done as a proof, as opposed to a proof that it is actually the truth. And this model, by the way, actually explains the excess everywhere now, everywhere on the sky. You see the excess and it can be explained. So, moderate changes in the electron and nucleon spectrum can then do it. And then, of course, you don't want to just look at the spectrum, we also then model the longitude and latitude distributions of gamma rays. And you can see it fits pretty well. We don't try and fit all the wiggles due to galactic spiral arms, but this is the pole and this is the plane, and you see it really follows pretty well the latitude distribution. There's still some excess here, mid-latitudes. I think it does quite well now. Okay, and here, again, we have a bit of an excess in mid-latitudes as you change the energy scale. So this is sort of current best model in that sense. And we get a bonus, actually. I mentioned that antiprotons. Now, if you don't use that optimized model, you just observe, you just take the spectrum which you observe. The antiprotons are predicted to be this red line with reacceleration model, and you actually predict too few in the conventional model. But if you take the spectrum which we're proposing, you get a bonus. You actually predict quite well then the antiprotons. Okay, that's shown in the next one. From the conventional model to this optimized model, the antiprotons get better and the positrons are also okay. So in some senses you win also with these antiprotons. Okay, that just summarizes all those things. And remains, of course, the more exotic dark matter idea, which should not be regretted out of hand, because maybe these changes are actually larger than what we're really about. Something more interesting could be possible. That's been published just quite recently, actually, quite a nice work I've been before. Something different now, and this is more or less the end. Something coming from the pulsar distribution. Now we're talking about the distribution of sources in the galaxy. And there's been a new survey, the Parkes Deep Survey of Pulsars, which has about 1,000 objects, and that allows you to get the distribution of pulsars in the galaxy. And this ought to be a measure of the distribution of supernova remnants, of course, because it ought to be more or less a one-to-one relation. So we know quite well the distribution of supernova remnants in the galaxy then. And there's a classic problem, there's an old mystery. And it goes right back to the cos B times. This is the distribution of pulsars which I just showed. But for gamma rays, up to now you've always needed something shown by the purple line there, actually very much flatter. So it's always been a real mystery. You know, if supernovae produce cosmic rays, how can it be that the gamma rays seem to suggest something like this, and supernova distribution like that? And very often people we said, okay, we don't know the supernova and distribution very well. But now it seems, you know, with this pulsar data, it's actually very hard. The problem hasn't gone away, it's got worse. And we think we have a solution. And the clue is the galactic metallicity gradient, for example, in O2H. We know there's a metallicity gradient in the galaxy, and we know the metallicity then decreases in radius. And there's been quite a lot of recent work on the relation between this relation between molecular hydrogen and CO with metallicity. And in fact, a lot of the gamma rays, about half the gamma rays, are actually coming in interactions of cosmic rays with molecular gas, not atomic gas. And so it turns out that for various reasons we expect this ratio to decrease with metallicity. So if this decreases with R and this decreases with metallicity, then the ratio increases with radius. So we've plotted it here. And basically, I Okay, I should remind you that for the molecular gas we're using CO surveys. You can't measure the molecular gas directly. So this ratio is very important for getting the molecular component. And if this ratio increases with radius, like this for example, we can actually compensate the variation of this variation times this, can actually then give something more like what we observe. So I've just written it here. The gamma rays we see are the sources times this ratio times CO, which is what we observe, plus the other things. And so if the sources then get steeper, but this ratio is flatter, the result can be what we observe. So we can actually save the supernova distribution just by allowing for this X gradient. And this was published, just came out in August here. So it seems to be the solution to that. And when it's quite a large variation in that ratio, by the way. And when you make such a model, then you can reproduce again the longitude distribution, agrees with the observations. And in fact, you even, because you have a more of a gradient in the gamma rays, you actually get an even better fit for the gamma rays at intermediate latitudes. So the fit improves globally as well. So maybe there's something in it. It doesn't prove that it's right, but it probably goes in the right direction. Okay, so the conclusions. Just to conclude then, the diffusive model, the acceleration model seems to work quite well, but it's not really proven. The height of the halo is about 4 kiloparsec. The gamma ray excess is probably caused by nucleon and electron spectrum which differ by a factor of a few relative to directly measured. And this has a bonus that it predicts the positrons and antiprotons better. And the SNR origin of cosmic rays is now consistent with the E-grid data considering the effect of the metallicity gradient. And for the outlook, well, more physical input. It would be nice to improve, for example, our magnetic field model. Maybe we can get input from this meeting for that. And indeed, cosmic ray propagation, which, as I said, is very, very simple phenomenological. We want to put more physics into that. Make truly self-consistent models like Dieter Breitschwert, for example, has been doing. And then use Galprop to test such models against all available data. And in the near future, in fact, what we're looking forward to is the Glass Gamma Ray Observatory, to be launched in 2007, which will be a kind of super egret, which will give us far better data. And we're starting to work on building models with the view of analysing that data. Okay. Questions? Questions, please.
As a comment to this diffuse gamma ray gradient, UV rays, maybe you remember that we published a model some time ago which actually tries to explain this by the fact that where you have a higher star formation rate, which means the supernova remnant distribution peaks, you also have a higher local galactic outflow, and that is of course causes hot gas plus cosmic rays to leave the galaxy earlier, so the diffusion is actually dependent on the radius of the galaxy, and this would remove cosmic rays efficiently, and therefore you would have less gamma rays produced, and this actually gives you quite naturally a flat distribution.
Right. I mean, it's probably maybe less required now. Yeah, the question of whether there are people who may not. We have to see what the experts are going to say about this X gradient. If it really turns out to be as large as we claim, you won't need your effect anymore.
But this effect is there. I mean, I think you can't discuss it away.
Okay, but
the variation of a ray, you have a higher pressure locally, and therefore you have a higher.
It's a good explanation.
So it is a physical explanation.
But this is also a physical explanation. So.
Yeah, but it depends on what you say is the distribution of CO in the galaxy, and
well, that's known.
But you have to assume metallicity gradients, as I understand.
Well, you don't have to assume them. I mean, there seems to be good evidence for metallicity gradients. That's definitely the case. What isn't so sure is how the ratios vary with metallicity. I mean, the pundits are telling me that it goes to Z squared. X goes to Z to the -2.
This huge hydrogen conversion factor has always been a mystery.
Yeah. Yeah.
So it's really difficult to prove that this would actually do the job.
It goes in the right direction, which was more or less what we wanted to say in this.
Sorry, wait a minute. we have a discussion today, right? I think you are talking about a very important thing. There also that there is another implication. That if indeed the cosmic ray gradient isn't as steep as the source, then we have a problem. But still, you assume quite a steep gradient of magnetic field.
A magnetic field is
but nevertheless, it's known to be steep. Then we don't have a competition between cosmic rays and magnetic fields. So the decision between which you can emerge from your discussion has far-reaching implications for the whole radiation astronomy. So I do suggest that we continue this discussion at 6 o'clock today. Right? It's a very important topic to discuss.
Yep.
Well, I just wanted to ask about this.
So let's do it in the evening, right? Because the question is there any sort of a competition between cosmic rays and magnetic fields? Because this, if indeed the cosmic ray distribution radius is as shallow, as uniform as gamma rays would imply, without any further thinking, then we are in trouble with the competition. It's strong trouble.
Well, we believe that the source distribution of the cosmic rays is more or less a supernova remnant of Hauser distribution.
Yeah, but before, you see, that was so badly known that you could more or less explain it away. But in the pulsar, you can't anymore.
I never did.
Yeah, no, you explained it, so it's even better.
So more questions. So let's leave this for discussion.
Okay.
It's too important to make the questions for discussion. Okay, then what? Next talk. Thank you, and thank you for very interesting and inspiring talk. We have finished. The title has slightly changed of Michael's talk. It's now Cosmic Ray Dynamics and Dynamo in Galactic History.
Okay. So I would like to focus on the description of the cosmic ray propagation in the interstellar medium. This is the title, The Cosmic Ray Dynamics and Dynamo in Galactic History. The work is done in collaboration with Katarzyna, Grzegorz Kowal and Harald Lesch from Munich. First, I would like to remind some very basic properties of the interstellar medium, since we are interested in the self-consistent description of the cosmic ray and interstellar medium dynamics. So, first of all, we know that the interstellar medium is multi-component, which means that it is a coexistence of many gas phases with a wide range of temperatures, also magnetic field of the order of 3 microgauss and the cosmic ray gas. So these are the three major components. Observations tell us that the three components, the energy density of these components is comparable, and this is a strong indication or maybe evidence for the dynamical coupling of this between these three components. So it means that if there is an excess of energy in one of them, then it is somehow distributed among the two other components. As we learned, the major source of ISM disturbances are the supernova type 2 explosions. There's a nice article by Mordecai Maclow, recent review of modern physics. The kinetic energy of supernova explosions is of the order of 10 to 51 Earths, and a significant part of this energy is converted to cosmic rays. According to different estimations, it is something like 10 to 50% of kinetic output from a supernova converted to cosmic rays, which means that this is a huge amount of cosmic ray energy. The rest of the energy is spread among the thermal heating of the ISM and turbulence. So what about the cosmic ray component? First of all, we have learned from the previous speaker that these are charged particles, protons, electrons, and many other particles, but for the present purpose we will focus on protons because they possess the most of the cosmic ray energy among the other components. The main galactic sources of cosmic rays are supernova remnants of the type 2. Then we know that the Larmor radius of cosmic ray protons of the energy of 1 gigaelectronvolt in 1 microgauss magnetic field is of the order of 10 to -5 parsecs. So it means that the cosmic ray protons of such kinetic energy, are practically tied to magnetic field lines. The cosmic rays, of course, propagate with the individual particles propagate with the speed of light. However, the cosmic ray streaming imposes instabilities in the ISM, and then turbulence, and then scattering of cosmic ray particles on the self-excited turbulence. Then this implies the diffusive propagation of cosmic rays with the bulk speeds of the order of the Alfvén speed. So, since the cosmic rays propagate diffusively, one can try to apply a kind of diffusion advection approximation for the propagation of cosmic rays in the moving interstellar medium. This is, of course, a much simpler approach than the one presented by Andrew Strong. So we assume a fixed cosmic ray gas, which is a relativistic gas. There is no energy dependence propagation, but on the other hand, there is the propagation dependent on the dynamics of interstellar medium. So in this way we can describe cosmic ray gas as a medium, as another component, which can be then supplemented. This kind of propagation of cosmic ray gas may be supplemented to the set of MHD equations, and then the complete dynamics can be studied with the aid of this equation. I come back to the previous slide. In this equation, there is a term which denotes the diffusion and also the advection. The advection term and the source, the adiabatic compression term. So, in order to describe the anisotropic diffusion, we should use a diffusion tensor. So we assume that the diffusion of cosmic rays is not isotropic. Quite recent papers by Giacolone and Giorgi relying on numerical experiments of particle diffusion in a turbulent magnetic field show that for a turbulent magnetic field of the same order as the uniform magnetic field, the perpendicular component of the diffusion tensor is about 5% of the longitudinal component, which the perpendicular and parallel means here the perpendicular and parallel with respect to the direction of the uniform magnetic field. So, in order to quantify this, we apply a diffusion tensor of this form, which was proposed by Ryu et al. In a recent paper about Parker instability in the ISM. So, basically we know that gas and magnetic field the motion and the dynamics of gas and magnetic field influences cosmic rays, because the shocks and turbulence lead to the particle acceleration. But on the other hand, we should take into account the fact that cosmic rays influence dynamically gas and magnetic field, because every scattering event of cosmic ray particles on magnetic fluctuations means a transfer of energy and momentum from cosmic rays to the gas component and magnetic field. So, if we want to implement the kind of fluid description for cosmic rays, we should also include the gradient of cosmic ray pressure in the equation of motion of gas. This is quite a standard thing. You can find it in, for example, a textbook by Brzezinski and al. Okay, so an example of this coupling is the Parker instability, which has been discovered by Parker almost 40 years ago. The cosmic rays and magnetic field and gas, when they are stratified by a vertical gravity, they are unstable. If we perturb such a uniform horizontal magnetic field with cosmic rays in the vertical direction, a kind of wave-like structure starts to grow, because the weightless components like gas and magnetic field support from below the heavy gas. So after such a perturbation, gas starts to slide along magnetic field lines, and the top regions of such magnetic loops are even lighter, so they continue to grow up. This kind of instability works even without cosmic rays, but if cosmic rays are an additional component of the ISM, the instability becomes much more vigorous. The reason is that the magnetic tension stops or slows down the Parker instability in case of lack of cosmic rays, but on the other hand, the cosmic ray buoyancy is not limited by any other force. So we find that the Parker instability with cosmic rays is much faster. Okay. Now I would like to go to a more detailed description. So first I define a reference frame. We deal with the magnetic field and cosmic rays and gas in the galactic disk. So in order to simplify things, I focus attention on a little rectangular box which is placed somewhere at the radius r naught from the center of the galaxy. So all the further description will be done in the Cartesian box, finally including the rotations, the rotational pseudo forces like the Coriolis force and the tidal force. So this is our reference frame, and now the full set of equations is the standard set of MHD equations. This of resistive MHD equations, where we can find all the equation of continuity, the energy equation for gas, the equation of motion with the cosmic ray pressure gradient taken into account, the rotational pseudo forces, the induction equation with resistivity, which appears to be quite relevant, and finally we include also the cosmic ray propagation diffusion advection equation with the diffusive term and sources of cosmic rays from supernova remnant. The diffusion tensor is here. I explained this before, so I don't stop and go further. Then the implementation of cosmic rays, of cosmic ray transport into the Zeus code. We do the simulations with this Zeus code, where the cosmic ray transport equation has been implemented according to the algorithm described in this paper. I don't go into details here because time is going on. And then some test experiments. What you see here is the magnetic field which is inclined with respect to the to this axis, so it is not sharp enough, I guess, but the arrows of magnetic field are directed along the diagonal of the box. At time equals 0, I inject some cosmic ray gas at the center of the box and start to and allow to evolve the system. So since the diffusion only along magnetic field is assumed here, so it means that the perpendicular component of the diffusion tensor is equal to 0. The initial Gaussian peak of the cosmic ray distribution starts to evolve to in this magnetic field direction, so we can see a kind of ellipsoidal distribution after some finite time. So this is done without, in this case, there is no gradient of cosmic ray pressure taken into account. So we can call it a passive cosmic ray transport. On the other hand, if this term is included, then we see that the results are slightly different. So there is not only the diffusion of cosmic rays along magnetic field line, but there is also an expansion of cosmic rays. Here again, we have magnetic field arrows and cosmic ray energy density. Here this is the density of thermal gas, and we see that at this time the cosmic rays make a kind of hole in the gas distribution, and some gas starts to flow along magnetic field lines. All this volume expands, the volume occupied by cosmic rays expands because of the contribution of cosmic ray pressure. Another example is the same experiment but made in a stratified disk. So there is a vertical gravity. We inject some portion of 0.3 of the 10 to 51 Earths of supernova kinetic energy output in form of cosmic rays and observe what happens. So first, cosmic rays diffuse along magnetic field lines. They inflate the volume. The volume occupied by cosmic rays is lighter than the surrounding, so the structure starts to rise, and we see after some time of 100 million years that there is a Parker loop formed by the input of cosmic rays into the horizontal magnetic field. So
How much energy?
0.3 times the 10 to 51 Earths. But this is only a kind of visualization, because in a real disk there is, in this time, in the time of simulations, there is more supernova explosions, so we go on. Now the question about the origin of galactic magnetic fields. There is a number of different ideas about the origin of the initial magnetic field in galaxies. One of them, which provides, according to my knowledge, the strongest magnetic field at the beginning of galaxy evolution, is the idea that the initial magnetic field comes from exploding stars which produce magnetic field, and then by the explosion they spread the magnetic field around in the interstellar medium. So the mean magnetic field in galaxy scale would be, in this case, of the order of 10 to minus 9 Gauss. On the other hand, the observed magnetic fields in present galaxies are of the order of 3 to up to 10 or even more times 10 to minus 6 Gauss, 3 to 10 microgauss. And we note that there is about 4 order of magnitudes of difference between the estimation of the initial magnetic field and the present magnetic field. So we conclude that there is some amplification mechanism necessary to explain this evolution of magnetic field during the life of galaxies. The currently standard theory of magnetic field generation in galaxies is the theory of turbulent dynamo, which has been proposed a long time ago by Parker, then developed by different authors and described in standard textbooks and review articles. This standard theory of dynamo has been strongly criticized at the beginning of 90s. So, as a reaction, Parker proposed another kind of dynamo which is driven by cosmic rays. The idea of the cosmic ray driven dynamo is simply relies on the effect of buoyancy of cosmic rays, assuming that there is an initial horizontal magnetic field lines in magnetic field in galaxies, and that supernovae explode, providing the thermal gas and cosmic rays. There should be some kind of magnetic lobes inflated by the hot gas and cosmic ray component. Then Parker proposes that these kinds of structures start to evolve and to reconnect. It means that the topology of magnetic field lines can change. So if the initial magnetic field is horizontal, then such kind of closed loops of magnetic field can form due to the reconnection, and then such loops could be rotated around the vertical axis or vertical axis to become more radial. So it means that in this plot, these loops are rotated by, for example, Coriolis force, and then they can reconnect again to form a large-scale radial magnetic field component. And then the differential rotation should amplify the toroidal component from this new, recently generated radial component. Okay, this is an example to show a kind of toy model which we published with Harald Lesch in 2000. This is the model which has been done in the so-called thin flux tube approximation. It means that we assume that there is a flux tube, a one-dimensional object, in which we can describe the cosmic ray diffusion. So this is our version of the Parker model. I could show you some animations with an initially horizontal magnetic flux tube into which we inject locally some cosmic rays. So, due to the expansion, inflation of this flux tube by cosmic rays, the flux tube becomes buoyant, and due to the Coriolis force in the disk, the rise and expansion implies the twist of the tube. So finally we obtain a kind of helical flux tube as a result of the cosmic ray action and the Coriolis force on this tube. On the other hand, we can imagine the following two tubes into which we inject cosmic rays. They start to grow, to form such Parker loops independently, but due to the Coriolis form twist, finally they start to interact because some parts of the tube collide. So, assuming that reconnection is able to change the topology, we can observe a kind of interchange of the ends of the tubes. So one part rises up with cosmic ray, the second part goes down back, and finally this part, which remains close to the initial position, starts to contain some radial magnetic field component. The initial configuration was the purely azimuthal component. Okay, but this is just to show the basic idea. Now I would like to talk about the most recent results we obtained in the three-dimensional simulations of the cosmic ray and gas and magnetic field simulations. So I would like to summarize here the basic elements of the model. First of all, we take into account the cosmic ray component in the diffusion advection approximation. Then we take into account localized sources of cosmic rays as supernova remnants. Then we assume a localized and uniform resistivity. In fact, in the simulation I'm going to show we applied only the uniform resistivity. And then we made simulations in the shearing box approximation. I mean, the shearing boundary conditions and tidal forces are applied in order to be able to model the part of the disk with differential rotation. Finally, we apply the realistic vertical disk gravity for the typical for the neighborhood of the Sun in galactic disk. Okay, now some parameters of the simulations. First of all, we do three-dimensional simulations in the Cartesian domain of the size 500 parsecs in radius, 1000 parsecs in the azimuthal direction, and 1200 parsecs in the vertical direction. From z equal to minus 600 up to z equal to 600. So the mid-plane of the galaxy is in the mid of the box. We apply the periodic boundary conditions in the azimuthal direction, shear periodic boundaries in the x direction, and outflow in the z direction. The disk rotation is typical for the Milky Way. I mean, this is twice the solar rotation angular frequency around the galactic center. And also we assume the rotation curve, the flat rotation curve with the shearing parameter Q equal 1. Then the supernova explosion frequency is 2 supernovae per kiloparsec squared per million years. The statistical distribution of supernova explosions is uniform in X and Y in the horizontal planes and Gaussian with the scale height equal to 100 parsecs in the vertical direction.
Now, this 2 kiloparsec squared per year is how many supernova per year, or for the whole galaxy? Just for the reference.
I don't remember because you know the distribution is varying very strongly with radius. So it is at the maximum, which is around 5 kiloparsecs from the center, is 19 supernovae per 19 per parsec square. So it is then one can normalize this somehow to obtain. So at the peak is 19, and I apply 2. Okay, and now the cosmic ray energy input is 10% of 10 to 51 Hertz per 1 supernova explosion. The cosmic rays are distributed in the sphere of the radius 50 parsecs. The initial distribution is Gaussian around the explosion center. Now, the diffusion coefficient. The most important, the parallel diffusion coefficient, is 10% of the realistic value. The problem is, one can use the realistic values, but since I'm applying the explicit algorithm for the cosmic ray propagation, the time step depends on the cosmic ray diffusion coefficient. The higher is the diffusion coefficient, the slower is the simulation. Then the initial condition is the magneto-hydrostatic equilibrium with a very weak magnetic field of the order of 0.9 times 10 to minus 9 Gauss. The initial cosmic ray pressure is equal to 0. the gas density is 3 atoms of hydrogen per cubic centimeter. The initial sound speed is 7 kilometers per second. And these are some pictures from the simulations. Here I show the gas density in colors and the gas velocity with arrows. So this is the slice along the azimuthal direction, this is along radius, and this is the horizontal slice at time equal 2000. Now I would like to show how it evolves with time. We start with this 10 to minus 9 Gauss initial magnetic field, and we inject cosmic rays. Here you see the effect of the cosmic ray dynamics on the dynamics of gas. You know that everything starts to boil very quickly, velocity fluctuates, and the gas density fluctuates. So nothing special is seen here except the fact that this all boils and that there is a vertical stratification of gas density due to the vertical gravity.
Is this gas density?
Yes, this is now gas density. Next animation will show the cosmic ray density, energy density, and magnetic. So, a long time, the amount of cosmic rays in the disk rises. So, and also the magnetic field becomes stronger. So, altogether, this leads to the thickening of the disk. The disk inflates due to the contribution of cosmic ray pressure and the magnetic pressure. Now we see the cut through the volume at time equal to 2000 for the magnetic field, the magnetic field and the cosmic ray energy density, again in the same cuts along the azimuthal coordinate, along the radius and in the horizontal plane. So now this shows quite an advanced stage of the simulation. P is the magnitude of magnetic field is indicated here. Here is around 2, but this starts from B equal 10 to minus 3 microgauss. The units of B are microgauss. Okay, so due to the cosmic ray injected locally in these red spots in the random way, the magnetic field starts to evolve, it fluctuates, and you see that on average the magnetic field strength is growing up from 10 to minus 9 Gauss up to a few microgauss. One interesting thing is that in the whole volume the magnetic field was directed into positive Y direction. Now inside the disk we have a positive direction, and in the upper and lower layer it is the magnetic field is reversed. Okay, but basically even though the medium is strongly disturbed by the cosmic ray input, we observe some dominating mean component of magnetic field. This is the vertical plot of the mean radial and azimuthal magnetic field averaged over horizontal planes. So the initial magnetic field is purely azimuthal. The azimuthal component is denoted with the blue line. The radial component is the red line. The radial component is multiplied by 10. So we start with the magnetic field of the order of 10 to minus 9 Gauss. And now look what happens. Along the evolution of the model, the magnetic field becomes stronger. The value, this is the maximum always here. So the magnetic field, the mean magnetic field grows steadily. Both the azimuthal component and the radial component. You can note that the peaks of the azimuthal component and the radial component coincide. So it means that we have a coupling between the amplification of the radial and the azimuthal magnetic field component. The final mean magnetic field is of the order of 2 micrograms. Okay, and what is interesting that we can see some kind of wave-like structure in the mean magnetic field, which is existing for almost all the simulations. So there is in fact no migration of, no visible migration of the mean magnetic field in the vertical direction. Maybe only a little shift of this maximum toward the upper and lower boundary. Okay, so that's basically all. Now only the plot of the total magnetic energy, which grows from time equal 0 up to 2,300 million years. We have an exponential growth in this range, and then the growth of magnetic field saturates here. Different X red, Y blue, and Z green components are shown. So the mean azimuthal component of magnetic field dominates. And here is the time evolution of the magnetic flux, which grows from some small value 1 in normalized units up to the value of 1,300 units, which means that we have an amplification of the mean magnetic flux by more than 3 orders of magnitude. Okay, and now we arrived at the conclusions. So, first of all, we made the first numerical experiments in which amplification of the large-scale magnetic field has appeared as a result of the solution of resistive MHD equations with cosmic rays described by the diffusion transport. So, the essential elements of the model were the continuous supply of cosmic rays into the ISM, the presence of differential rotation, and the presence of explicit resistivity. We found the amplification time scale of the mean magnetic field about 250 million years, which led to the amplification of B of the mean magnetic field by almost 4 orders of magnitude in 2 gigayears. Okay, so the final conclusion is that the Parker's type cosmic ray driven dynamo works very efficiently, that the magnetic field of the large-scale magnetic field exceeding 1 microgauss should be expected in very young galaxies, since we needed only 2 gigayears to obtain the strong mean magnetic field. And it seems that observations of damped Lyman alpha clouds performed by Wolf, Lancetta, and Oren seem to confirm that there is a large-scale magnetic field in objects of the cosmological redshift about 2. So that's all. Thank you.
Thank you. Questions, please.
Because I have a question. At the beginning of the talk, you underlined that the magnetic diffusivity is important.
Yes.
But then I couldn't find the
magnetic diffusivity.
Magnetic diffusivity, eta.
Yes.
What is the value of the eta?
This is the value of eta is equal to 1 in scale units. So it does not say much, because the problem is that when we want to make simulations with a finite grid resolution, we have to adopt somehow the resistivity to the grid resolution. Yeah, so there is a kind of artificial resistivity. The value of eta, which was taken in this simulation, exceeded by a factor of few the artificial resistivity. So it means that it was relevant in the simulation. However, it is quite difficult to rely this to connect this value to some physical value in the interstellar medium. The role of resistivity is to provide some here.
No, only the number.
Well, I don't remember exactly how to translate it to
10 to 26, like the diffusion.
Oh yeah, yeah, okay. Yes, 1 times 10 to 26 centimeters square per second.
And the viscosity is 0.
0, yes.
And you show
Strange one,
results
number.
of eta.
Yeah. This is the turbulent value of the eta is the turbulent value of
No, the eta is the resistivity of the medium. It is not a turbulent.
Yeah, 10 to 26 is the turbulent value. Centimeters square per second.
Sorry, 1 times 10 to 23.
23?
Yes. Because 1,000 units is the turbulent resistivity.
And the next question.
No, I guess it should be bigger. You have Reynolds number of the order 50, right? With your resolution of 50 mesh points, 50 is roughly your Reynolds number that you have in your simulations. So the resistivity you can afford must correspond to Reynolds number of 50. So your resistivity can be only 50 times. Let's estimate. Then if your box size is 1 kiloparsec, typical velocity speed of sound 10 kilometers per second divided by 50. 1 kiloparsec divided by 50 is divided by 10 is 1/5, 10 to the 26 centimeters square per second, if I'm not making that mistake. This must be your numerical resistivity corresponding to resolution of 50.
To the Reynolds number.
The Reynolds number 50. So the Reynolds number 50. So the Reynolds number is the size of your box times the speed of sound divided by your theta on you.
You mean magnetic Reynolds number?
Whatever that matter. There must be the same model.
We should check it later.
Another remark.
Okay.
Even if I watch your figure 3, this is the time dependence of your vertical profiles of the magnetic field. I find that you start with a 1 cell initial field, and even after the first time step, this is not your first in the numerical sense, but other.
Excuse me, I don't understand that.
Yeah, in the second one, you showed it.
Yeah.
Even in the first next plot, you have 4 cells. And say remain the whole time. So you start with a maximum V phi at the equator, and even after the first there's 0. It must be very characteristic.
It is not 0. It is much less than the initial.
And nevertheless, it must be very characteristic for your dynamo regime that the toroidal field at the equator is immediately minimum if you start calculating.
Because there is a continuous pumping of energy which removes the magnetic field from the equator.
Yeah, and this is my point. I'm afraid that after a while the dynamo switches off by this effect.
Apparently there is a drop.
Yeah. And the last observation is always in your computations, the toroidal field exceeds the toroidal field of the radial one by a factor of 10.
Yes.
That means the pitch angle is
Quite correct.
always. It's very characteristic for
Yeah.
and this is my point. Maybe it has to do with the amplification is too strong. It has to do with your eta. If you change the
It
eta,
is too small or too large?
no, the radial fields become too. No, the toroidal field is too large by a factor of 10.
No, that's why too large.
In order to have a pitch angle of 55 degrees. In the observation or the real galaxies, the pitch angle or the radial magnetic field and the toroidal
In
magnetic
this
field.
case, this is on the average something like 10 degrees. 10 degrees.
No.
Yeah. Okay, 10.
1/5, 1/10.
Yeah.
I checked the...
So there was kind of question first.
So, a very basic question, I might have missed something, but the cosmic rays go in with this diffusion and fraction approximation, and they don't have energy losses. Is this right?
No, don't have energy losses.
And
It
the
depends on
box
the
is the box is periodic, so they go out one side and come in the other. So you're continually feeding this energy.
No, the upper and lower boundaries are outflow boundary conditions.
So they
However,
actually leave just by that.
Yes, they can leave, yes, of course.
Okay.
Well, just reacted on your value for the supernova rate. You said 2 supernova per year per second, square per million years. That seemed to be very low to my recollection, and I found a figure in for year 98, which has a peak at 130, not 20, but the peak is 130 at 5.
I just also made this
I don't exactly remember the number, but it's assuming that I followed her paper in this.
I have it in front of me. That's
Okay, you can check it later.
It's my estimate. I also made this estimate, and I was worried. It seems that for the whole galaxy, this corresponds to one supernova per 700 years,
Yes.
in contrast to 30. So your supernova rate, unless I made a simple mistake, is a factor of 20 lower than in reality.
Okay.
But then there must be no dynamo. If you reduce driving by factor of 20, then your turbulent velocities must be correspondingly lower. There must be no direct connection to this supernova rate. If the parameters are
The
correct.
turbulent velocity was typically at the advanced stage of the simulation of the order of 3 kilometers per second.
No, that's also the upper instability which brings in the turbulence. It's not only the supernova.
This is the rate of energy injection. If you inject too little energy,
Yeah.
you will be lost. However you use this energy, unless you have an efficiency factor more than 100%.
But if it becomes magnetically unstable, then you get some additional turbulence, like shear instability.
So the problem is probably that the corresponding energy loss is missing. The main energy loss is cooling. Do you have the standard?
No, there is no cooling, in fact.
Right.
No cooling. Only the advection and the diffusion out of the box. But concerning the distribution of the cosmic ray in energy input or supernova rate, there is a peak around 5 kiloparsecs, and then the supernova rate drops suddenly up to almost 0 at the solar rate.
At 16, no, at 16.
Okay, but if you have in front of you the paper by Katia Ferrier, you can see that the radius of
But this cannot compensate factor of 20 difference, It can result in factor of 2 or 3 difference between the solar circle and the maximum. But
according to her model, the supernova rate is much lower at the radius of 10 or 8.5 kiloparsecs from the center than.
But it's still
than in the mass.
It's still 20 or 30.
Do you have the rate per cubic parsec or per squared parsec?
This is
Square
just for
parsec.
square parsec.
Okay. So in this case, it's
Well,
much
20 would make sense to me. To 20, then it's equal one supernova per 70 years, which is it's 1 per 30 for the whole galaxy. Locally, it's factor of 2 lower. Okay, acceptable. But factor of 20 is too much. Miguel, you have a question, I think.
Yeah, I would like to see the movies again.
Okay.
Possible. That's the question.
Which one?
One on the left.
Cosmic rays with magnetic field, yeah?
Do you have any density movies? Temperature? You want to look at it?
No, temperature, no. Density, gas density.
Can I see the gas density?
Okay.
Is there any, do you have, for any chance having a movie with the scales, the color scale is fixed? Because
Not here. I can do it.
So what is the largest density you have in the...
Now it is one particle per cubic centimeter. The scale means, yes,
Yeah, I see.
the density, the maximum density in the box is going down because of two factors. One is the disk inflation, and second, we have still some losses of gas, but not very significant through the upper and lower bondar. So in open bondar conditions.
Okay, so this is 2.3 gigahertz, right?
Yes, this is 2.3 gigahertz.
Okay, so you have a maximum density of 0.66 on Right. Can you show me the first frame now?
Yeah, it was 3.
Yes.
Okay.
3. Okay, so what is the mass loss you have on the boundaries on the end of simulation?
Here is something like 20-30%.
Yeah, Peter?
If I understand correctly, the magnetic field connection plays a crucial role in this dynamo. You didn't mention what kind of mechanism you use. Is it Pechak mechanism, also we target really?
At this level of accuracy, it is just reconnection.
But I mean, this should matter for the amplification part of the dynamo.
Yeah, in fact, this resembles more the fast reconnection because in some independent experiments with reconnection, we observe the inflow of matter, of gas, into the reconnection region with the speed of which is a fraction of the speed of the alpha speed.
But then you need some sort of standing shock wave to compress really the gas hard to get.
Yeah, this is concerning reconnection. This is not as accurate as simulations which are dedicated for the reconnection, because we have not enough resolution for that.
It's any mechanism that produces that sort of resistance.
Yeah.
Whatever mechanism now can produce it, it's
It's serious in the sense that you want to look at what times when you can actually amplify the dynamo. If you have not the connection that is fast enough, you're lost.
Yes, if there is no resistivity, the evolution of the system looks quite different. So the resistivity is quite essential here, because without resistivity, there is a very fast growth of the random magnetic field component, and here we have this does not.
Okay, Axel?
I'm interested to see the effects of cosmic ray conduction. That wasn't very clear from the animations, because in the animations we saw that you injected energy in the cosmic rays, that led to bubbles in the cosmic ray energy. You would then expect, if diffusion along magnetic fields is important, to see some correlation between the cosmic ray energy density and the magnetic field, which I didn't see.
No, not directly, because first effect is after the cosmic ray injection is the diffusion of cosmic rays along magnetic field line. Yeah. So the cosmic rays spread very quickly along lines, the magnetic lines, and then there is due to the expansion and due to some kinetic perturbation, the flow pattern becomes turbulent, and on average the cosmic rays move up to the upper and lower boundary.
So you say it was really too fast in the animation?
Yes, it was too fast because the input injection of cosmic rays was done at times equal 0, 0.5, 1, 1.5, and so on. And the frame was done just after or in the mid of, just after every second injection of cosmic rays.
There is a related point to this. To understand correctly that your diffusivity of cosmic rays only depends on the direction of magnetic field, but not the magnitude.
Not the magnitude.
So if magnetic field in the expanding bubble, of course it decreases. Still the diffusivity of cosmic rays remains large there within the bubble.
Yeah.
You might expect that, but is it true that in reality it also should decrease with the magnitude of magnetic field?
It should depend, it should be, the diffusion coefficient should not be too large in the explosion region in order to keep particles close to the shock, yeah, and then, okay, but I don't know exactly. But I can confirm that the diffusion coefficient should depend on local conditions.
Should we discuss it during the discussion today or tomorrow? It's an important question. Funny. Just wondered what, you're losing some, Miguel pointed out, you started at maximum density plot here.
Yeah, this is the
3.4 is your initial.
Yes.
Have you got any plot time series of B squared for the whole box over rho? So You know, I assume there's no way for magnetic energy to be removed from the box.
Yes, it is, because the upper and lower boundaries are open.
So they can allow magnetic field out with matter.
Yes.
Good.
Did you make a check of these calculations if you switch off the supernova explosions after some initial growth?
No, I did not.
What magnetic instabilities will you do?
Magnetic and cosmic ray, because they cosmic ray.
Okay.
Yes, that is a good idea, but I did not do this experiment.
Even more questions.
I mean, a related experiment would be, of course, to say, what if you inject all the energy as thermal energy only? You would still need get a similar driving, because you would inject, I mean, you would basically produce a gas pressure gradient rather than a cosmic ray pressure gradient, and the only difference then would be that you don't have conduction along field lines, which I was still not so very convinced that is very important in this mission.
Yes.
So the question therefore would be, with thermal driving as opposed to cosmic ray driving, would you not expect to get something still rather similar, or are you sure it is actually decidedly different?
The basic difference is that after a single explosion here in cosmic rays, the cosmic rays spread along field line without producing a shock. So they fill, the cosmic rays produced locally fill in the space very quickly, while the hot gas is surrounded by the shock, and still the cold medium exists. Yeah.
Is
So
it like a supernova explosion along the magnetic field?
cosmic rays diffuse very quickly. So it means that in 1 million years, the cosmic rays fill in space along, something like hundreds or thousands of parsecs. 1 million years after the explosion.
But anisotropic.
Anisotropic, of course. So there's no shock.
Yeah, I mean, directly related to this, I think I have to contradict here, because we see in our simulations where we simulate the ISM by supernova explosions and follow the evolution of the magnetic field and the gas, etc., that you have very strong turbulence that you create, that the magnetic field is actually dragged out into the halo, and you form large loops. And I think I would agree with Axel that this process should be faster in most cases than the cosmic ray-driven dynamo. I mean, in any case, you should take it into account to see whether this cannot be just a few cosmic ray-inflated gas bits, because you don't confine a super bubble to a magnetic field. That's not possible in 3D. You always create holes where you can actually drive flow.
But on the other hand, nothing can be more buoyant than cosmic rays.
Yeah.
Even hot gas, however rarefied it has weight. Cosmic rays have no weight. In this sense, buoyancy due to cosmic rays will produce faster vertical velocities than anything else. Except this direct velocities of the order of 100 kilometers per second, which Franz can't advocate for the base of the fountain.
But it's a matter of the pressure gradient, and that, I mean...
Pressure gradient can only produce sonic velocities, right? No pressure gradient can produce velocity larger than the speed of sound.
No, the problem is always the overpressure
Oh no, it can.
to the ambient medium. And that is what actually then defines the pressure gradient, and that is what defines the outflow. I mean, I think this is basically true what you say, but I think the time scale that you need for inflating loops is probably longer with the Parker instability than you have if you have a breakout of a superbubble.
I think that there are very important differences. One is that, for example, the filling factor of the hot gas and filling factor of cosmic rays. So maybe, it is very hard to answer this question, but I think that there are still differences.
We have just 1 minute. We are discussing this for more than half an hour now. Last question.
In the language of the mean field dynamo theory, in order to model an electric dynamo, you need a big alpha effect. Or a large alpha effect. And the alpha effect becomes large if the correlation time becomes large. Larger than one supernova explosion is. This is the reason that Katja over here moved to the superpowers. Increasing of the correlation time by a factor of 10. Then also the attraction, the escape velocity is smaller than the alpha effect. This is good. Can you, in this language, can you explain why it works now? Do you increase the correlation time in some sense?
The correlation time at the beginning is of the order of 25 million years. of this at the beginning of the simulation at the weak magnetic field. At the end is of the order of 50 million years.
Well, but usually,
The lifetime of the supernovae?
50 million years.
50 million. Yeah?
well, here the scale is different. Here the typical scale is not 100 parsecs, but 1 kiloparsec. And this, of course, comes 1 kiloparsec.
Yeah.
And this also, of course, affects all the estimates. Here, the scale of parking stability is 1 kiloparsec.
Yeah, but
100 parsecs.
concerning of the scale of the
Crystal turbulence.
of the fluctuations, maybe this is important. After the Fourier transform in the azimuthal direction, it is order the maximum of perturbation energy is around 300 parsecs. Not 1 kiloparsec, but less. The maximum, but the spectrum is very wide.
Coffee is waiting. Thank you everybody for the exciting discussion.
Yeah, so coffee should be normally in the cantina, and the local people should guide you and open the door.
Oh, we can use the basin.
Or you can use the basement, but there you also need some guidance on the right direction, that direction. Unless, of course, the coffee is okay, but I don't think so. Check.
Someone